It's newtons, everything newtons. Newton's law, applications of newtons, right? Okay, so let's keep going, and there is a review, right, in the Dropbox. So it's 20 questions as usual. Okay, so make sure you understand also friction, right? So if you have static friction, the body is not moving, and the applied force equals to the static friction until you reach a maximum. So the equation that you can use here, it's only true for the maximum static friction force. And that will be equals to the coefficient that depends on the two materials in contact times the normal force. And normal force does not have to be equals to the weight. Normal force is how hard the surfaces are squeezed together. So if you are pushing on the block, it will be the component down of your push plus the weight, okay? And then you see static friction, it gets to a maximum here, and then it's going to decrease once it's moving, and that kinetic friction here stays the same. So with the dummy, for example, we have seen that the dummy is pushing, it's going to push back, pushing back until it's going to reach about, I think it was like 125 Newton. And finally, friction decreases, it's going to move, and the kinetic friction is about 90 Newton. Okay, so I want to make sure that is clear. And then don't forget that for every action, you have an equal and opposite reaction. The consequence, good morning, is not the same, right? So for example, here, action, reaction, you see, not that you want to do that demo, but I thought it was cool. The force will be the same, right? So the force applied on the projectiles, on the bullet, will be the same as the force applied to him. But the consequence is not the same. The bullet will accelerate more than the guy. So for every action, you have an equal opposite reaction. You cannot push harder than you are being pushed, and you cannot be pushed harder than you are pushing. Okay, same thing here. For every action, you have a reaction. So the force will be the same. The consequence is not, because the acceleration of the exhaust gas will be larger than the acceleration of the space shuttle, because the space shuttle has so much more mass. Okay, so these kinds of questions, conceptual questions, I don't go over the review, right? Because it's conceptual questions, so I cannot give away everything. Another example, I think I show you that. Okay, you need a lot of muscles here to do this, but it's also action and reaction. It takes a lot of momentum to do that, right? It's not that easy. So he's pushing, and the water is pushing him back. Okay. One thing I didn't show you is about friction. If there is no friction, nothing can move forward. So it's not going anywhere because you have not enough friction. There is not enough friction. So the reason why you can walk is because you push on the ground. So that will be static friction. So the ground is pushing back on you forward. Okay, so where did we stop? Last time we went, I was going a little bit fast here. Friction, okay, we talk about that. So you see, you go from static friction, then you go to kinetic friction. Very rarely that sometimes it can happen like Teflon on Teflon, then you go straight to motion, right? There is no static friction. It's just there is no transition. But it's very rare. Okay, so we did all that, and we were struggling with this one. So I want to go over this one. So for the test, it won't be that hard, right? But if you are a physics major or going into mechanical engineering, that's why you have this assignment, which is a little bit more challenging. They are fun to do, right? So if you have something like this, I think that I forgot what was given. You have kinetic friction, what was given. Okay, so kinetic friction was given, it was 0.3. This is 5 kilograms, and they want you to find the acceleration. So there was no friction between those two surfaces. There was only friction between here and there. So if this is your system here, you want to look at the force acting on it. So you have the driving force here, okay, which is 50 Newton, and it's accelerating down. So this one is winning. You have the tension, but if you take everything inside the bag, you don't care about the tension. Unless if you want to do it in 2 steps, which you can. And then you have the tension here inside the bag. They are killing each other, so we don't worry, it's inside the bag, it's privacy, you don't want to look inside. But you have some force here apply from this one. Okay, so that will be some kinetic friction. There is rubbing happening. So that tension has to be a little bit larger because there is an acceleration. And that tension here is the same. Okay, so you have kinetic friction. That kinetic friction is from this block to that block. Agree? So we already did that. So we say the winner is the 50 Newton. The one that is slowing it down is that kinetic friction, which is the coefficient times how hard they are squeezed together. And what is pushing on it? So what is pushing on it is the 120 Newton. Okay, it's easier to think that here you're going to put the squeeze. Okay, so 120 is squeezing, more hooking. And then here you have the total inertia, the laziness, which is 5 plus 9, 5 plus 9 times the acceleration. Okay, and if you do that, you find that the acceleration is 1 meter per second per second. Agree? And then it's all about using the right bag. So now if I am interested in this one is not moving, okay? It's not accelerating. Only this system here is accelerating. This one is just hanging there. So it must be in equilibrium between two forces. If it's not going anywhere, it means it's in equilibrium between two forces. So one forces, of course, will be the tension here, which is another tension. So I'm going to call that T prime. And for every action, you have an opposite and equal reaction. So then you have also a kinetic, you have another frictional force between them. Because for every action, you have an equal and opposite reaction. So the tension prime will be just that force here, which is a nu times 120. Is that clear? So those two blocks are in contact. Block number 1, okay, is acting on block number 2. And so this one is acting on that one, and that one is acting on this one. So for every action, you have an opposite and equal reaction. Agree? Yes? So if I'm just looking at those two blocks, right? So you have this block. So let's call that number 1, and let's call that number 2. No, number 2. So you have a force from number 1 here, F1 on 2, and you can see that because it's slowing it down. If it was not there, it will go faster. And you have a force from 2 to 1 because you cannot have an action without a reaction. So it's a pair. But when you're going to use Newton's second law, okay, you cannot put those two forces in a bag. You have to define your system. Hmm? Yeah. Yes, exactly. Like the wagon. Exactly. You cannot have your system with the two action and reaction applied. Okay, so let's do number 2 because you have something like this, I think. Let's something similar. Now I lost number 2. Just to know if you understand. So something is when you have friction, something is moving. If you can overcome, the maximum static friction, you have to overcome. Once you overcome it, then you switch to kinetic friction, which is always smaller. But first, when you apply a force, you need to overcome that maximum static friction. Okay, you can play with the dummy. It will not mind. So 50 kilogram here. And let's try to do this one. You apply a force here. So that will be your apply force. So this is you here. And you are pushing. You are pushing. I'm going to call that the push here. And it says that's going to be 250, right? And this is 30 degrees. And the magnitude here is 250 Newton. So you can always make a cross at the end of the vector. So you visualize the X and the Y axis. Okay, so you know in which quadrant you have your force. And what else do you have? You're going to have the weight. The weight is down. So that will be 500 Newton. And you have the normal force. But the normal force is how hard it's being squeezed. So it's being squeezed for two reasons. Because there is a component pushing down and it has the weight. So the normal force has to be bigger than the weight. It has to be bigger than the weight because you are also pushing down. So you see here you have two components. I don't know how to make the component. You have the Y component pushing into the ground, and you have the X component trying to make it move. Agree? In addition to that, you have some friction, but you don't know. We have the coefficient, but we don't know. We don't know which one to use because we don't know if we have been successful in making it move. So we have to figure this out. Okay, so let's find my push, my apply force along the x-axis. So it's going to be 250 cosine 30, which is, thank you. What's your name? Louis, yes. 216.5. So we don't know if 216.5 is enough to overcome static friction. So we need to find that static friction max to see if we are able to go over it. And if it's enough, then we can move to kinetic. But we don't know. So let's say 0.4. So 0.4 times the normal force. But the normal force is how hard the surface is being pushed on. Very good. Exactly. Right? So it's going to be 0.4. How hard? You have the y component here, so it's going to be 250 sine 30 plus the 500. Very good. So 250 Newton. So it's 250 Newton. So do I overcome it? No. So it's not moving. So it means it's not moving. So it means that what's going to happen? First of all, the acceleration will be equal 0. It means that the static friction will be equals to my push. It's not moving, right? Because until you reach that maximum value of static friction, whatever you are pushing is going to push back. So nothing is moving.
So it's asking us what the frictional force is. We find out whether or not we beat static friction, and then if we don't beat static friction, it's the same as our push, right?
Exactly. Exactly. So it's a tricky question because mathematically it's not that hard, but it's a tricky question.
We have no stop.
You have to find first. Yes. So in your university physics, you have all kinds of those type of questions, like little bit tricky, but it's very important for physics majors or mechanical or civil. You see, if you push, it's going to push back. So your static friction equals to your applied force until you reach to maximum, which is about 125. And then you have kinetic friction taking over. Kinetic friction is always the same. It does not change in value. Even if you let go, it's not going to change. And now you have a negative acceleration. Okay, so we already talked about that. Most important here is to understand that the acceleration is in the direction as the largest force. So this is the largest force, so the acceleration will be down. Here you open the parachute, all of a sudden you have a lot of air resistance because the surface area has increased. So the net force and the larger force will be up. Okay, so that means the acceleration will be up even though you are going down, and it will reach a new terminal speed because as you're going to slow down, air resistance will slow down as well. Okay, so it's not that obvious. We talk about that, so you can jump from an airplane with a parachute. It's going to be about 10 miles per hour. You're going to hit the ground. It's not the acceleration that kills, it's the change in velocity, right? It's the landing. Uh, there was a series called A Thousand Ways to Die. Someone jumped from an airplane but survived because you still have some air resistance. Not that you want to do that, of course. A lot of engineering here, when you have those cyclists here, they make a race. They have a race, so the air drag depends on the speed square. It depends on the fluid. If the fluid is like air, then it depends on the speed square. If the fluid is like corn syrup, it will be just the speed. So anyway, it depends on the speed square, it depends on the density of air, it depends on the surface area. So that's why here you want to have a aerodynamics shape. So the surface exposed, okay, will not increase the air resistance, and it depends also on the shape. So all these are engineering, okay? This is not physics here. You have to do experiment and trial to define those constants here. Except for air density, it has to be measured. So what they do, they go one behind the other one. So that way he will be shielded. Okay, so it will be less tiring for him. And then they take a turn and they change position. Isn't that smart? And so there is this very famous video. You got to love. Did I show you this video? No? You got to love the Italian, okay? I love Italy, I love Italian. You need to have the core muscles to do that. I don't know if you realize how tight his body is. You need a lot of muscle. Right. And then you have to go back. She's also very hard not to fall. Extremely hard. Look, it's not that easy. Wow.
Because usually whenever I take my feet off, I end up accidentally falling right.
No, it's very hard. So anyway, okay, so object in equilibrium, accelerating object. You can use the book way or you can use my way. On an inclined plane, when something is going down slope or up slope, you always have the component of the weight mg sine trying to pull the body down slope. Mg sine, that will be equals to mg cosine, always for inclined plane. Okay, so we did this one. That's going to be on the test definitively because it's a very easy problem to understand what is your system. Okay, so this definitively, you can make it even more headache if you add some friction. But it's the same idea, right? So if I put this one in a bag, it's going to be applied by a pulling force. It's going to be applied by a kinetic friction force. And it's going to be applied by a tension. So you're going to have 30 minus 8 minus the tension equals 4 inertia times acceleration. If I put everything in a bag, which is 6 kilograms, what's happening between them is privacy. You don't want to know. Like some students, they send me email. No, I had a fight. Da, 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 da. I cannot do my homework. I don't want to know. Okay, you need an extension. It's fine. Okay, so here you put that everything in a bag. That will be your pulling force. Then you have the friction, which is 6 plus 8 equals mass, which is 2 plus 4 times acceleration. Okay? Okay, so we did those kind of problem as well. Okay, so you have the driving force that just will be the weight. If there is no friction, you're going to have the weight equals the total mass times acceleration, and that's what you're going to get. Okay, we did that. So those kind of problems here, you have a YouTube video. I forgot the channel, but he's very good. So with this kind of problem, sometimes you don't know which way it's going to move. Is it going in this direction up slope or is it going down slope? So you can give yourself a direction, says, okay, let's say it's going up slope. So the acceleration will be that way or this way. And if you find the negative acceleration, then you know that you got it wrong and you have to start over. Got that? Okay, because you don't know. Sometimes you have to find the forces first to see what's happening. Okay, so let's see. So first of all, I like to put everything in a bag. I'm gonna go fast, right? So you see here what he does. He already divided the weight, so that will be your weight here, into two components. One is along the slope, so that will be your x component here, trying to make it this way. And you have the y component here. And you always take the acceleration. You don't know which way. If it's this way or that way, you don't know. And here you have the weight and then the tension. So what is the drive? This force. Okay, let's find this force. So this force is the mass 1.3. So it's going to be 1.3 times 10. So it's going to be 30 Newton. So it could be the driver. Okay, if it's going this way, that will be the driver. Are you with me? But we don't know. And what is the loser? The loser is that force here, right? This force here, make it go down slope. And that force here is M, the mass, A, G sine 50. Okay? So, and that force will be 27 Newton. So these are the two forces in competitions if you put everything in a bag. This one doesn't have impact on the motion. It's just up and down. So which one is the largest? Mg sine. Okay. So that's how we know that this one wins. It's a competition. So this one wins, which means the acceleration will be in this direction. Okay, so then we can say the winner, which is 27, minus the loser equals inertia, which is whatever you have in the bag. So it will be 3.5 plus 1.3 times the acceleration. Okay. Now, if you go to if this is confusing, you go to YouTube and he explained it a different way. He's gonna get you the two equations with two unknown. And you have acceleration is 3. I think, okay, if I didn't do any mistake. And then if you want, you can focus on this system here. And it's going up. So you can say T minus 13 equals 1.3 times 3, and you can get the tension. Okay, that's one way to do it. You don't have to do it this way. If it's going up, this one is winning. So now I can put this one in a bag. Okay, so I can decide now it's going to be this one in a bag. Any questions? It's good. Okay, otherwise you have this video here. Okay, so we did all that, right? You have two ways to do it. So here they are doing the two equations with two unknown. You focus on this one and then you focus on that one, or you can put everything in a bag. And the winning will be the F cosine. Okay, the F cosine, okay, is the winner, minus this one is slowing it down, so minus m2g minus the kinetic friction. So you have a lot of variations. If you don't like my way, you can look at here. They do it only algebraically. Okay, so you can take your time and do it. And then you have all kind of torture instruments for students, right? Then you're gonna pull your hair. So this one is interesting because it says if you push really hard, okay, you push very hard on the surface is gonna push back on the body. Okay, so this is inside your bag. This is the apply force. You push on the surface. The surface is like made of little springs. So it's being squeezed. So it's going to push back. That will be called the normal force. It's on the wall. And then because you push, you're going to have some static friction here. And then here you're going to have the weight. And you have all kind of problem, interesting problem. I like to put everything in a bag, but if you don't have to, but the main idea is to decide what is the system you are looking at. Once you have your system, then you look at all the forces acting on this system. That system has to be touched, except for Mother Earth that has a power to grab, at a distance. But otherwise, if you put A in your bag, you want to say, okay, it's being touched by P, you're going to have a normal force, you're going to have a tension, you're going to have the weight, and you have some static or kinetic depending if it's moving or not. So very important to understand the system. Okay, are we good? Okay, so then we go back to circular motion. So again, here we consider constant speed. So it's a constant speed, uniform circular motion. So a typical question, by the way, on the test, typical question for a conceptual question, like everything is all over the place, so I'm not sure where it is. Here. So that will be one of the conceptual questions, you see. To make something go along a circular path, you need a force which is called a centripetal force. So it comes from this here, right? It's going to push the ball inward. Once there is no more force applied to it, it wants to keep going along a straight line at a constant speed. Okay, it's not going to curve anymore. So it's like that stupid movie, Wanted. There is no such thing as a curved bullet, right? It keep going along a straight line at a constant speed. Okay, so if you want the thing to stay on a circular path, you need to apply a force. That force is called a centripetal force. If you have a force, you need an acceleration because the acceleration is the force per unit mass. We already did that. You can check, you can use geometry to show that acceleration will be v squared over r. Okay, v squared over r. So if you double your speed, if you're making a turn, you need 4 times more force to stay on the highway. Otherwise, off tangent you go. Be careful driving today because it's the full moon. I don't know if it's today or soon. People become cuckoo, okay? You have to be careful. So that will be the velocity, always tangent to the trajectory. That will be your centripetal acceleration, meaning your force per unit mass. Centripetal means looking for the center. That will be the equation for that, v squared over r. An equation, we already did all that, just a review, right? mv squared over r. So if you have, for example, something like a ball going zoom, then you can feel in your gut that if you increase the speed, zoom, so then you're going to push harder on the surface. So the surface is going to push harder on you. You're going to feel very heavy as you make the turn. So how do we solve those kinds of problems? And you have one question like this for the test, is that you always take, for a circular motion, you always take the acceleration to be in the positive direction. So you say, okay, acceleration is here toward the center. The acceleration is always toward the center. So the largest force has to be toward the center. That's the rule. Okay, the largest force is always in the same direction as the acceleration because that's the winner. So if you go zoom, you have the normal force that will be large and you have the weight. So when you do zoom, you're gonna feel heavy.
It's the edge of it.
Very good.
Pushing back.
Exactly, because it wants to keep going in a straight line at a constant speed. No, you can't. So it's being pushed toward. Okay, and faster you go, harder you're gonna push toward, which make you sick in your stomach. If see, you're gonna feel very, very heavy. It wants to keep going straight line at a constant speed. No, you can't. It's gonna be pushed toward. So the push toward has to be larger, always. Otherwise, off tangent you go. Okay, let's do something very easy here. You can see as it's going to increase the speed, the tension here that you can measure will be larger. So a centripetal force has to be provided by something. So here it's provided by the normal force. And like the demo I just showed you, it's a normal force. You push on the surface pushing back. Here it's from the strain. Okay, so this is that comes from my algebra class. But it's good to know the fundamentals, right? So you need a tension here to provide the centripetal force. So it doesn't mean centripetal force is always a tension. It depends. You need something to keep you on track. Otherwise, off you go. You want? No, you can't. You can't. So you are falling toward, right? So the acceleration will be v squared over r. Think of acceleration as a force. It's a force, centripetal force. It equals mv squared over r. So it will be 0.9. The speed. So here it's not a vector, it's just a speed over 17. Which is yes, 19 Newton. Okay. So of course it's not intuitive that you say, okay, the acceleration is toward the center, but you have to remember that acceleration is what? It's a force per unit mass. Sometimes it's easier to remember this. Acceleration is the net force per unit mass. So net force and acceleration have the same direction, which is not that intuitive. What do you think about that? So it's swinging. Is it harder just to hold her, or to make her swing? To hold it is harder than just hold and swing?
Oh, sorry. I think when it's missionary, it's
Huh? Hold and swing is harder. Okay, makes sense. You can feel it in your gut, right? So if you have like this, um, okay, let's forget about the guy. I'm gonna focus on her. So if there is no swing, she's just holding there. holding that, let's say it's like an acrobat here, here. If there is no swing, she will be acted by her weight, okay? And then you have the tension up there. So you see that the tension here equals her weight. Okay, what's gonna happen if she swings? So now you're gonna have still the path here. You're gonna have the trapeze. I don't know if it's called the trapeze. Let's say you have a rope here. But now there's a velocity, right? There is a speed, so she's moving. So if she is moving, her body wants to keep going straight and at a constant speed. No, you can't. You need a force here. You need an acceleration. You need that centripetal acceleration. So that means you need a winner in this direction. That winner will be the tension in the arms of her partner, and that's going to be the weight. Okay, so when you have a circular motion, you need a winner that will provide your centripetal acceleration, that will provide that force pulling you in, otherwise off tangent you go, and she'll make a projectile motion here and ouch. Okay, so you need a winner T minus mg equals m v squared over r. So not only the tension has to balance the weight, but it also needs to provide the centripetal force. Otherwise, off tangent you go. That's why it's very, very hard. That's why usually you have the guy here and the lady there, because you need a lot of muscles here. It's not that easy. It's actually very hard. Okay? We have seen this example as well, right? So if you want to create artificial gravity and it's spinning, okay? The body wants to keep going straight at a constant speed. No, you can't. It's going to be pushed by the wall. So the centripetal force will be provided by the normal force. And if you don't want to have osteoporosis, you want that thing to spin the right way, so you will feel the same as gravity. So mv squared over r will be equals to the normal force, and you want to be equals to your weight. And that's how you can solve those problems here. But we already did that. Okay. And if you are making a turn, what is the force that keeps you on the curve? Friction. Static friction. The car wants to keep going straight at a constant speed. No, it can't. Okay, you're gonna have static friction. And if it's not banked, so if it's not Daytona race or whatever, if it's flat, so you're gonna say static friction is what is gonna provide the centripetal force. That's why you don't want to go too fast, because if you multiply the speed by 3, you need 9 times more static friction. And if you go over that maximum static friction off tangent, you're dead. Right? And then static friction will be equals to, of course, the maximum one. The maximum one will depend on the normal force. So that will be static friction. Okay, the next problem is always in the textbook. So I'm not going to go into details, okay, because you can open your textbook. But this is the Daytona Beach or what, North Carolina, whatever, the race. NASCAR. The NASCAR race, right? So we could, in theory, do that without any friction. Why? what is it pushing? So the car goes around this circle here. What is it that is pushing the car? The normal force. Excellent. Very right. What's your name? Eli. The normal force. The normal force. You don't need friction. You don't need friction. You could drive on ice. It could be icy, that's fine. Because the normal force here, the normal force has a component pushing the car in. That's why they do it this way, so they can go really fast, like 200 miles per hour, like crazy fast. Okay, so I'm going to do it quickly. Don't worry too much. It's just interesting. So you have the normal force here. Because it doesn't go up and down, I don't need to have the normal force, I don't need to take my x-axis here because it doesn't go up slope or down slope. But remember that you always want the positive direction in the same direction as the acceleration. So the acceleration will be toward the center. That's where I want to take my positive direction, right? The car wants to keep going straight line at a constant speed. No, it can't because you have the normal force. So in that case, in those types of problem, in that case, I'm going to take my x and y this way. Why? Because I like to have my x-axis always along the acceleration when the problem is complex. So this is plus. So my acceleration has to be along the x-axis. And then you have a little bit of geometry. You can use that theta here. So this angle here is the same as that one. Are you with me? Okay, this angle here is the same as that one. So the one providing the centripetal force, it's going to be the normal, the component, the x component. Can you see that it has two components? You see that? So the normal force has two components, x component, and it has a y component here, and you have the weight. Are you with me? That's why components are so important. That will be how much of a force is along the x-axis. That x component, it's going to be n, I think it's a sine, equals, that will be your centripetal force. That component here is pushing the car toward the center, otherwise off tangent it goes. The y component is busy balancing out the weight. So in engineering or those type of classes, when you see a sine and a cosine, you get itchy. Okay, it gets very itchy because you say sine over cosine is a tangent. So you really want to divide 1 by 2. Okay, so that way you're going to have 10 equals mv squared over mg. Ah, okay. It's always the case. When you have a sine and a cosine and they are isolated, you really want to divide them together so you have the 10. It's the same thing like we did to find the coefficient of friction. We did tan for the tangent also. Okay, but don't worry about this one too much. But you can see here they have a nice drawing and you get to this equation here. So you know what's gonna be your maximum speed so you stay on track. If you go too fast, off track you go. If you go too slow, down you go. So you really need to have the right speed. That's why the NASCAR, it's not that easy. They need to know to learn the guts. Guts learn physics so they stay on track. Okay, so let's take an example. What's going to be your speed here? So you already have the equation. Okay, so the tangent of this angle equals v squared over RG. I go a little bit fast. Okay, that's because it's an old textbook. So this textbook here comes from, that one comes from the college algebra. But you get the idea. Okay, what's the equation? Tan equals V squared over R. Any question? Where is NASCAR? It's in Daytona Beach and what? North Carolina? Huh?
Indianapolis.
Oh, Minneapolis.
Indianapolis.
Indianapolis. Not North Carolina. No? Indianapolis. Indianapolis.
Track down. Opposite.
Indianapolis. Okay. RRG. There is a G. Okay, there is a G, right? Which is what? Okay, do the computation. Do it. 43. Yes, yes, yes. R is 316, 10. Okay, so V equals 40, about 44, which is about like 100 miles per hour. And in reality, they go much faster because not only they have the normal force pushing them in, but they also have friction. They also have static friction. So because they have the push from the normal and the static friction, then they can go really fast, like 200 miles. I don't know what's the record. 200 miles, because otherwise you're gonna fall. You're gonna fall toward the center, which you don't want. Any question? Okay, 96 miles per hour. Blah, blah, blah. Okay, that's on the test. Why don't you try to do it? I'm not going to plug the numbers. I just want to get to the equation. I just want to see the algebra. So this is called a conical. I don't know if I say it right. It's a conical pendulum, like this. This is something like this, right? Like this. Okay, this is a conical pendulum. Conical, thank you. Conical pendulum. So it's stay on a circular path. Yes?
Do you see about the ice?
The what?
The ice in the moon?
Oh, France is done. Okay, don't say that. But France, it's done. Can you believe that? And it doesn't make sense. The Louvre, they take their time. They have a truck, like it's old-fashioned truck, a truck with something that is lifted like a platform. They take their time. They arrive to the Louvre, cool. And then they make a U-turn, very cool. And then they put things on next to the tires, right? So it doesn't go away. And then they go and they break the glass and there is a siren and there is tourists, but no problem, they break one of the jewels and they take the jewels and they go. Huh? 4 minutes, yeah. I cannot say any comment because I can get in trouble, but it's pathetic. It's very pathetic. And then they say, oh, we thank all the people, the security guards, like the security guard. They were doing this, and they were taking video. It's really, really, really down, down, down. France is going down train. Really, really, really bad. If you want to have nice vacation, you don't go to France. You go to Italy, for example, much better. It's a shame, it's a shame, it's a shame. So anyway, what will be the forces acting on it? The weight. And then, yeah, the centripetal force, you're right. We need a centripetal force, but something is providing the centripetal force. The what? So the weight and then the tension. Very good. So you always think, what is my system? My system is this thing, the marble here. What is touching it? The tension. The string is touching it, and Mother Earth. That's it. And then you say, okay, it's going around a circle at a constant speed, so there is no acceleration along the path, but you need an acceleration. Yes. So along here, there's no acceleration, but you have a centripetal acceleration. So you want to take always your acceleration along the x-axis. So we're going to take the x-axis here, and we're going to take the y-axis here. So each time you have a circular motion, you want to have a x-axis along the acceleration. The acceleration is a centripetal acceleration. So there is an acceleration this way. So that will be plus. So that centripetal force is provided by what? The tension. Okay, the tension, it doesn't come from, it has to come from somewhere. The tension has two components, a y component here, and it has a x component. So it's the x component, okay, that provides the centripetal force. Of tangent it wants to go, okay? It wants to keep going straight and at a constant speed. No, you can't. But you always take the x-axis, positive here, and the centripetal acceleration along that x-axis, which is v squared over r. Okay, so now you can do, so it will be always along the x-axis. Okay, I'm going to put x-axis. Okay, so this is the plus. So we have only the x component equals mv squared over r. Okay, so the acceleration here is centripetal. So you could say ma. I can say ma, except that that acceleration is centripetal. And along the y-axis, you're going to have up equals down. And here you don't have right and left because it's only left, the winner. And then you have T, so the tension, T sine. Is that sine or is, yes, this is sine. This is cosine, and this is sine. Sine theta equals mv squared over r, and you have T cosine equals mg. Okay, so you get itchy? Hmm? Do we have? Look, for now, I'm just doing algebraically. You divide, right? 1 over 2 because you are itchy. Look, you have a sine and a cosine. sine over cosine. So sine over cosine equals this over the reciprocal. Okay? When you divide, you multiply by the reciprocal. Any question? So you have tan equals v squared over rg. So you get the same equation as for the bank, like the Daytona Beach. It's the same equation, v squared over rg. Because it's a good question. Because before we had the normal force, and instead of having the normal force, we have the tension. But it's the same geometry. So you have the weight down, and here instead of having the normal force, you have the tension. The y component is balancing out the weight, and the x component is providing the centripetal force. So you can memorize it if you want. Okay, and what else? You have the radius, so this is gonna be the radius here, and that will be L. So I don't know, you can say tan equals opposite opposite is R over adjacent, and adjacent will be square root of L square minus R square, right? This side here. Depending on what is the question, but that's the idea. Okay, so any circular motion you're gonna need something to provide the centripetal acceleration. And here you have an example here, and they do the computation. You can compute the acceleration, which is v squared over r. Okay, you can compute the speed. And your textbook 5.20, I try to put the problem. So it will be unit 5, which is applications of Newton. It's good, especially if you want to go mechanical engineering, it's good to look at different approach. Okay, so this one, we already talked about it. Also, making a turn. It's making a turn. So what is providing that centripetal force here? So yeah, kind of. So it's an action-reaction force. So he's making a turn. You can have a lift. So the lift here. And here you have the weight. But it's the same, kind of the same thing, because it's only the x component here of your lift. X. So you push the air is pushing back. The x component is making that turn happen. And you have the y component here, which is busy balancing out the weight. So it will be that component here equals to mv squared over r. So that's why it's doing this. So you cannot say that the centripetal force is always the tension. It's provided by something when you are making a turn. Okay, you are changing the direction of the velocity. Okay, so something like this will be on the test. So you have different variation. I'm gonna ask you how help each other talk to each other. It goes zoom, and you can feel that if you don't go fast enough, you're losing contact. The normal force equals to 0, and you're not going to make it. You need to go really fast. Faster you go, more normal force you're gonna get. Now remember that the normal force is always perpendicular, but always from the surface to the body. From the surface to the body. From the surface to the body. Okay. So the centripetal force has to be provided by something, and that's going to be the normal force. Very good. Very good. Harder is going to push, larger will be the normal force. So I'm asking you to draw the forces acting here, and then there, and here, and there. In all the cases, draw the forces on your notebook. Draw the forces in each case and write down your equation. So you can help each other. And remember that acceleration, x-axis plus. Acceleration is toward the center, toward the center. So I'm looking here. So I want to have the positive direction here. You can take your x-axis here toward the center. That will be toward the center. So I need a winner. I need a winner toward the center. So where is the weight here? Straight down. And where is the normal force?
Straight up.
Up. From the surface to the body. From the surface to the body. So this is your weight, and the normal force is the winner. It has to win. That's why you're going to feel very heavy. So the normal force, the winner minus the loser, equals your mv squared over r. So the normal force has to overcome the weight and provide you with enough centripetal force. Okay? Because when you go really fast, you push very hard on the surface. Yeah. You can do that when you have like a loop, right? You take like a car, you go this way, but then if you push really hard, you can feel how hard it's pushing back. What about here? Where is the weight? Down. Where is the normal force? Very good. From the surface to the body. And obviously you need some thrust. I don't know how. Hey, you need some, yeah. Unless you have some momentum, otherwise you have the thrust pushing. And so here, the only one providing the centripetal force will be the normal force toward the center, toward the center. What about here?
Weight.
So weight. And where is the normal force? Down. People wants to say up. No, 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 no. From the exactly from the surface to the body. Exactly, and that's how people get it wrong, because now plus will be in this direction. So we're gonna have the normal force plus mg equals mv squared over r.
Yes, it's still
You need the normal force. What's gonna happen if there is no more normal force, if you don't go fast enough? You fall. So we can find the minimum speed that you need, otherwise you're going to break your bones, right? If the normal force equals 0, because you're not pushing hard enough, then you're going to have mg equals mv squared over r. And guess what? We get again the same equation. V squared, not the same equation, no. Rewind. V squared equals rg. Mg equals mv squared. So v squared equals rg will be the minimum speed that you need not to lose contact. If you lose contact, that's it, you're dead. Bye-bye. What's going to happen is that it's not that you're going to fall. It means you keep going straight line at a constant speed, then you're going to make a nice projectile motion. Any questions? It's not that easy. You need to understand that, you see, you always take positive toward the center, positive toward the center, positive toward the center. And then we have what it's called loop the loop. So loop the loop, you can do the computation that I did, and you get to this. You need a minimum speed to make loop the loop, otherwise you go off. So there is this YouTube video. I don't know, it's if you are very sensitive, maybe you don't want to watch. Okay? So he did it, right? So that you need enough speed to make it. It's not that easy. Because otherwise some guy, that's what happened to him. I don't know, have you heard of him? I hope he's okay. I hope he's okay, okay? There has to be a guy to do that. I don't think they know what they are doing, okay? Oh my God. Not 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 good, right? So that's why you need physical therapy, okay? Physical therapy is a very good field, okay? Because we have those crazy people. You see, normal force equals 0, and then off tangent he went. He doesn't fall straight down. Off tangent he goes. Okay, so you can do the computations here. So if you look at history, when they started to build those rides, like like the Ferris wheel and all those rides, a lot of accident happen. And I guess at the time you didn't have all those law firm to sue people. A lot of accident happened. So they had to make it very safe. Yes. Kinetic friction? Yeah, you should take kinetic friction. So here we suppose that there is no kinetic friction. Yes. Yeah. No. Okay. So here you do so do you understand here? Everyone agree with me? Yes? Okay, let's go to the test. Let's go what it's called a Ferris. Wait. You should ask. Go on Google and ask, what at the time how many accidents happen. Many accidents happen. Okay. So can you so this is different, right? So we have a Ferris wheel. Okay. Hope I say it right. And we have someone inside sitting. So I'm focusing on this person here. I'm focusing on this person here. So that will be my focus. So if
the weight total and the weight.
okay, so in that case, so I forgot if the test use this situation or that situation. It's not the same. One of them. Forgot. Okay, so I'm focusing on him or her, and she's sitting or he's sitting. I don't know. So what are the forces acting? The weight. So weight is easy, okay? It's gonna be straight down. But where is the normal force? Is it going down or up? She's sitting. I'm putting her in my bag. She's sitting. Only her butt is touching the seat, right? Yeah, so the normal force has to be up. You touch the seat is touching you back. But you see, I need a centripetal force. So this here has to be larger. So typical conceptual equation, when you are drawing on scale, you want to make sure that mg has to be larger than your normal force. No, now I'm just putting this lady inside my bag. So just the lady. So the lady, you have the weight and the normal force. Why is the normal force less than your weight? Because you need a centripetal force winning. It has to win. It has to be larger to provide the acceleration. So if you have an acceleration again and again and again, you need a winner. If you don't have winner, it's just gonna be not going to accelerate. You have no acceleration. If up equals down, you have no acceleration. You need a winner. You need a force here. You need a net force. So that means that mg, the weight, has to be larger than the normal force, and that will be equals to mv squared over r. This one has to be larger, which means that you're going to feel very light. Normal force is your apparent weight. So if you sit on the bathroom scale is going to read less. If it's moving, obviously it has to be moving, right? You need to have some moving happening. Okay? So that means that your normal force, your apparent weight, will be your real weight minus. And you know that if you go to this ride, you feel your stomach, you feel butterflies in your stomach. That because you feel that you're gonna fly off. You might fly off if there is no seat belt. That's why you need a seat belt. What about here? So you're gonna have the weight, okay, no problem. The normal force here, no problem. You're not going up or down, it's in balance. What is providing your centripetal force here? You need a force. What is pushing you in? I mean, it depends. If you have a seat belt, it will be your seat belt. If you don't have seat belt, your body, it's gonna it's gonna move toward the wall here. The wall is gonna push back. Okay, so you're gonna feel in your frame of reference, you're gonna feel pushed outward, right? You push on the seat, and the seat is gonna push back on you. Now here, now you have the weight mg, and again you need a winner. So in that case, the normal force is the winner here. You see, it's not the same thing. You're gonna feel heavy. Normal force in. So imagine this for the test: in minus out equals mv squared over r. You need a winner here. That will be the toward the center. So in minus out equals mv squared over r. So now you're gonna feel very heavy. Imagine that. You can go to Miami, right? They have a Ferris wheel. You go, butterfly, I'm flying. I feel heavy. Right? So in minus out equals mv squared over r. In is toward the center. So toward center. In, so that will be for circular motion. See, she's sitting, normal force here, that will be the weight here. And here it's the weight winning, more normal force will be smaller. Okay? Oh, we are almost done with the unit, so that way, that's it. It's for the test number 2, we're done. Test number 2. So perfect. Test number 2 is on Tuesday. Next Tuesday. And then we start it's the next. Oh, I thought it was next Tuesday. I'm ahead. Shall we move it to the 28th? Because you're gonna forget. It was supposed to be the 28th, right? So anyway, let's keep it to the 4, and we're gonna start a new unit. Okay.